Cool. Okay. Good to see everyone. Goal for tonight is to teach you guys a little bit about how to conduct collaborative programming. The things that I'm about to show you today, we'll sort of take it through. I'll take you through an example of how you might implement a new feature inside of Architect, which is Optics' trade-off analysis tool. And in doing so, I'll highlight some of the best practice workflows for engaging in software development on a team of our scale. So we'll tackle this through a very practical example. The ticket that we're going to try and tackle today, and I'll share my screen for this, is the following. So can you guys see my GitHub screen? This one here?
Yeah, we can see it. Well, I can see it.
Cool. Right. So this is Architect. This is the repository. GitHub, for anyone that isn't aware, is a code repository and source control platform. So you think of it like a Google Drive for your code. It's much more than a Google Drive, but the end concept of this is the same. It's a cloud storage website for your code, and the way that you interact with code on GitHub is a little more advanced than something like a Google Drive. So I'll show you a little bit of that today. The issues that we track for Architect, they're done through this tab on GitHub. So an issue is anything that any features, any bugs that need to be fixed, or features that need to be added. We typically track those through GitHub issues, or tickets, you might hear them called. So we have a list of tickets here that some of us are working on currently as part of the development for this tool, Architect. We are sort of moving away from this, and now we're tracking tickets more so in as chapters instead of Notion. But the ticket in particular that I want to tackle today for this practical example is I want to implement. Hold on, let me find it. Optical component. Let me look at the Optics Slack. We have an integration that automatically pings the channel whenever a new ticket has been added. So here it is. I want to add a component for Snell's law. So description states, added an optical surface component that can compute the angle of refraction for an incoming rate of light according to Snell's law. So for anyone who isn't aware, Architect is more or less an object-oriented library of sorts that contains mathematical models, as in like Python classes that contain mathematical equations that are relevant to some modeling of the optical components on the payload. And so this is a very simple example. We want to implement a class in Python that can compute the angle of refraction for an incoming ray of light. Okay, so that's what we'll tackle today. Let's say I was, of course, the original author of this ticket. I would go in here and assign this to myself, so the team knows that I'm working on this. There's no labels, no projects, and milestones. And we'll come back to this when we're finished the code, and we're going to put in a pull request. I'll show you how to do that as well, and link this ticket to that pull request to say, hey, this code that I'm offering to the repository fixes this issue or solves this issue. Okay, so let's dive in. That was how to assign yourself tickets. The next thing we want to do is, of course, download the repository, or we say pull the repository. To do that, I'm going to hit this big green button called code. I'll go ahead and open this in GitHub Desktop, which is another application I've already installed. Okay. It seems like I might have already installed it, actually, or downloaded it. Right. I think I forgot to delete this folder. Let me delete this and start fresh. So we show you the full process end to end. This lets me delete. Wow, this is huge. Oh, okay. It's not letting me delete. Anyway, I'll make a new folder then. We'll call it temp. And I'm going to clone the repository into this folder, temp. To do that, let me head back into GitHub Desktop. I'll do clone repository. I'll choose the folder I want to clone it into. So we said let's put it under workbench temp. And the one specifically I want to pull is, again, architect. Let me search for that. There it is. Okay. That's how you clone repositories. I'm going to go ahead and open that in Visual Studio Code. VS Code is a very nice IDE to work within. So I highly recommend that you guys check out VS Code if you don't already use VS Code. The first step, whenever you download any sort of code repository, is, of course, to set up your environment. And typically, the instructions for how to do that will be found in the README file. So always best practice to pull up the README on any new project you download. And typically, the READMEs will contain instructions for how to set up your environment. So we'll go ahead and follow the instructions to the T then from here. So open up an integrated terminal and go through step by step on the setup. So I've already installed Python. I know I have the correct Python version, but if I didn't know for sure, I could check the pyproject.toml file that specifies the Python version I need for this project. So right now it looks like we need between 3.10 and 3.11. And I can confirm which Python version I have by doing Python -- version in the terminal. There we go. Perfect. 3.10.5. I know I have Git installed. This Poetry is the it's the package manager of choice that we use. So you guys might be familiar with pip if you've taken an intro to programming. Pip is again a package manager, but it's not an environment manager. Poetry is both. An environment manager, oh, here's the dog, is effectively a tool that lets you create virtual environments within your application. And a virtual environment is basically just like an isolated container onto which you will install all the dependencies for a project. The reason you might want to install dependencies into a virtual environment, as opposed to just like your local machine as doing pip install, is that typically when you're working with multiple projects, each project might need its own specific dependencies, right, to run properly. And so you don't really want to install all the project's dependencies onto the scope of your entire machine, because then if you jump into a new project, you might have the wrong version of that package installed. And so that program will run correctly, and then it'll run to fix that by installing the correct version, but then your other project won't work. So virtual environments are a very nice way to containerize your projects. So that's what Poetry attempts to solve. So I've already installed Poetry, and I can check to make sure that that's the case by running Poetry -- version again. There we go. I got 1.2. I've already cloned the repository, done that through GitHub Desktop. The next step is to run Poetry install. This is going to go through the pyproject.toml file, this one here, in which I've manually specified all the dependencies that this project relies on. So that's AstroPy, NumPy, Pandas, Python, of course, and this other package called plot, as well as some development dependencies that don't actually factor into the final code base, but they are nice for development. This takes about maybe 2 to 3 minutes, but in the meantime, I want you to notice this pop-up on the right here. You notice the new environment has been created. Do you want to select it for the workspace folder? Yes, I do. What's happening here is that VS Code detected the creation of this guy, this new folder, .vm. This is where Poetry is currently going in and installing all of my dependencies. And it's asking if this is the virtual environment that I want to load up whenever I open the project or the terminal, which is exactly what I want to do. So every package that you're seeing listed here, these are all dependencies of my main project dependencies. So like NumPy might have some X number of dependencies from this list. It's going through and installing all those sub dependencies as well. So when this is done, you'll notice that we'll be able to pull up or interact with any of these packages within the terminal environment. Also, I'm going to go try and get through all this quick, because there's a lot I want to show you, including some new features that GitHub is rolling out. As of like fairly recently, they had their GitHub Universe Day last week. There's some cool stuff coming on the pipe. So no promises, but if we get to that, we'll get to that. But feel free to stop me if you have questions. I see Rosie has her hand up. Yep, what's up?
Yeah, I've got a question. So how do you create the file that determines what the dependencies are for that particular, like, sorry, no, not, yeah, what the particular packages required are for a particular virtual environment that you want to make.
Yeah, so these are specified manually. So these are packages that we deem necessary as part of the development, because like, say I want to interact with arrays. There's, of course, NumPy is useful for that. Pandas, again, for data frames, and plot this library for plotting. AstroPy is a movements library. So in that sense, you pick the packages that you want to use for your project, and then Poetry will handle installing the sub dependencies of these packages. That's why there's more to this list than just these 5.
Okay, so you need to create a file called like pyproject dot whatever that, I can't see it very clearly. Whatever that like file type is.
Yeah, pyproject.toml. Yeah. You create this manually. You could also generate it automatically by running something like Poetry add AstroPy. And if this file does not already exist, it'll generate it for you and populate this field AstroPy with the latest version that it finds online.
Cool. Just like a follow-up also, like last time we tried to get everybody to install Poetry, though, it was kind of like a nightmare to install. Is it still like that, or has it been like improved upon by that development team? I haven't revisited it since then.
Nope, it is way more stable, like super more stable.
Oh yeah?
Yeah, I remember it being a bit of a hell trying to install Poetry on people's machines. Ever since version 1.2 came out, so the version I'm running now, it's been a lot more stable, I'd say.
Okay, that's good to know.
Yeah, I think, but around the time that we started implementing Poetry into our workflow, it was a very young project. That's why I suspect we have trouble with it. Anyway, yeah, it's fairly stable now. Okay, so I've installed the current project. We see that here. And now pay attention to what's happening next. So I've got in my terminal here, I don't know if you can read that, PowerShell and the name of the directory I'm in right now. If I trash this terminal and open up a new one, the shortcut I'm using to do that is Control tilde. Notice that it boots me into this virtual environment, architect-py 3.10. What that means is that any package that I installed just now, I have access to. So if I go into an interactive Python terminal and I do import AstroPy, perfect. There it goes. I've imported AstroPy. Now contrast that to something like, let me open up a fresh command prompt. Oh, that's going to boot me into architect again. Let me just open up PowerShell up here. If I try doing Python again, import AstroPy, again, no module is found because this package only actually exists within this .vm folder. It doesn't exist at the root of my my operating system, so it's not visible to any other parts of my machine. Okay, so we've confirmed the install went smoothly. What's next? I've already done step 6, configure ID interpreter virtual environment. That was the step with the do you want to select a virtual environment for Poetry. I just hit yes, that's done. Then the last step here for the setup is to install my pre-commit hooks. So this might be a new concept for some of you. Pre-commit is think of it like a framework for running scripts before your Git commits. So if you remember back to programming 101, Git is your source control management tool. So whenever you write any code into the repository, it'll populate your changes inside of this source control. We'll see that in a second, but it'll populate your changes in source control. And you'll hit commit when you're ready to commit your code up to the cloud. So back to GitHub, the original repository. Pre-commit lets you set up a pipeline that will run on your commit. So when you hit commit, a series of scripts that you define will run. Typically, well, at least for our case, we use pre-commit to run things like auto formatters and linters on our code. So an auto formatter is a script that will auto format, like the name implies, all your code according to some coding convention. The nice thing about auto formatters, the really nice thing about auto formatters is that they're a very nice modern way to keep your code consistent across many development teams. Like if you're a large team, it's hard to enforce, best practices. And so getting the auto formatter to just auto format your code to the best practice is best for everyone, right? And then of course, the flip side here is that pre-commit can also run linters. So a linter is again some other Python or some other script that will check over the code and ensure that there isn't any outstanding, anti-patterns that you might find lurking around in the code that aren't necessarily fixed by the auto formatter. So that's where you go in manually and fix. Okay, I see that you left this stray comment here. Maybe consider removing it, and then you go in and remove it, and then the linter passes. Pre-commit won't actually let you commit until pre-commit passes all those checks. So it's a good way to check that you're only getting clean code coming into your cloud repository. So I've done that. I've installed pre-commit, and that's it. So that was the whole install procedure for setting up this project. Okay, 726, good. Next, let's take a look at the problem statement. So we wanted to implement some sort of class or component inside of Architect that contained the functionality to compute effectively what is Snell's law. So typically the workflow for us on the optics team has been twofold. First is you develop a mathematical model for what it is that you want to implement in code. And so that takes place inside of Notion. We have a very nice mathematical modeling database set up to do this exact kind of work. Right here. Each of these cards in the database, these are essentially like little equation cards. So they are individual units or equations that we implement inside of Architect, and we describe them and model them here. The reason we do this outside of the code implementation is that it's much nicer to work with LaTeX, especially for the more complicated equations, and it's much easier to write out long derivations for more complicated things like SNR or that signal noise or any other number of complicated things. But in our case, we care about this angle of refraction equation. I modeled this out earlier. It's basically just Snell's law, but I rearranged to find theta 2. So that's the outgoing angle for a ray passing through an optical surface or between two mediums. So the way these equation cards are laid out, you've got a nice diagram that shows you the physical meaning of every variable inside of this equation. Of course, you've got the LaTeX breakdown. Notion makes it super nice to work with LaTeX. You literally just write LaTeX as you would here. We break down, of course, the name of the variables, the parameters in this equation, as well as the units, which is super important, as we'll see in a second, to work with our AstroPy library that handles units inside of code. So we have the variables listed. We describe any assumptions that are baked into this formula. We trace our derivation here. So if we had to derive something manually from a base source, so in this case, it's Snell's law, I linked Snell's law here, and I show you the derivation, how I got to this final form. So everything is traceable end to end. Okay, perfect. So let's get going with that. While I'm here, I'm going to take the link of this page because this will eventually end up inside of Architect. And I'm going to go in here and figure out where exactly we need to create this class to make this happen. So the very first thing I like to do is go into my docs folder and take a look at the classes.png diagram. So this is a visual breakdown of the class structure inside of the program. We use object-oriented programming a lot. We leverage it pretty heavily. For anyone who isn't aware, very basic crash course, OOP, or object-oriented programming, is a method of organizing code in a very physical, tangible way. And the way that Architect is structured is everything in Architect is a system here. So here, let me see if I can zoom in. Up here is the system class from which all other classes derive, including components. So what this is saying is that system is the parent class. Here is a component class that inherits from the system class. And whenever you have classes that inherit from each other, this is basically just saying that this component class, an instantiation of this component class, can access any function of the parent class. So I could be, working with a satellite component, and I could call the component get dimensions functions. get dimension function, and it would work because the satellite is a child of the component class. So it's a nice way to structure code according to the domain of which your class is scoped to. So in this case, Architect is currently a very optics heavy tool, and so we leverage optical components a lot here, and we have children of the optical component like our hyperspectral imager. That's this guy here. That's the payload effectively. And things like lenses also inherit from this optical components class, and our for optics inherit themselves from lenses. And there's some other goodies in here. Anyway, so what I want to do right now is figure out exactly where I want to put this class in this hierarchy. So it's an optical surface component. And so it might make sense to put this somewhere along the optical branch, right, of these optical components. I know that eventually this component needs to end up somewhere here, like as a child of the optical component class. But for now, just keep things simple. I'm going to just make it a child of the component class, just the raw component class. Okay, so we've defined that. Let's actually run the implementation then. So I'm going to go into the source folder. That's Architect. I'm going to head down to Systems. I'm going to head into Optical. And I'm going to create my component. I guess I'll make it right here. So let me get a new file. We'll call this optical component. Oh, I see there's one here already. Optical component. Sorry, we're not making an optical component. That's already done. We're making an optical surface. Okay, so let's do that right here. Yeah, alongside optical component. New file, optical surface.py. Okay, so here we are, fresh slate. Let's define the class. So in Python, we define classes with class. We'll call this optical surface. I've got GitHub Copilot installed, which is why it's giving me some autofill. Okay, so what do we need this to do? We want this class to have a method for computing Snell's law. So we want to implement this equation that I defined earlier. So let me put these side by side. The zoom thing is kind of getting in the way. Okay. Define. Let's call this angle of refraction. Yep. What's up, Rosie?
So just to clarify the terminology, a method is essentially the exact same thing as a function. It's just a function that's within a class, right? Whereas you would call it a function if it was just like a function by itself, but a function defined within a class is called a method.
Yes, that's exactly right. Yeah, that's the only distinction in Python. This is your class. This is a function, but it's a method of the class. Yeah. Okay, angle of refraction. Okay, so what is, who can tell me what my variables are that I'm going to pass into this function? Based on the parameters you see listed here. I'll give you a hint. It's not every variable you see in here.
Feel free to just like unmute and like say it if you want.
All right, well, I'll give you the answer. We want to pass in θ1. We'll call this the incident angle. We want to pass in n1. We'll call this the incident index. Now, the reason we're not passing in everything here, including n2, is because we actually want to leverage this object-oriented paradigm to effectively have the class contain members, so variables of the class that define the optical surface itself. So a parameter of this optical surface is itself going to be n2, which is the optical or the call it the surface index or medium index. Medium index. This is going to be a property of this class, whereas the incoming ray angle and the incoming index into this, object, the surface, these aren't properties of the class itself. Like this is part of the external environment, right, of the surface. And so we don't care about that. We want that to come in through the function, but not be a property of the class itself or the object itself. Okay. So let me add a self here. We pass the self keyword so that we can reference these properties in here. And let me start writing some of this code out. So we want, okay. Copilot's giving me the answer. Great. Snell's law. It's returning mp.arcsign. We're taking the arcsign of the incident index, which is correct, multiplying it by the sine of the incident angle over self.medium index. Perfect. Okay. Now you'll notice I'm missing an import here. This mp thing is my NumPy library that I alluded to earlier. So I'll import that. What else am I missing? We, of course, want to be able to instantiate this class with some index associated with it. And so we'll call this medium index. We can pass the index in. We'll define it as none, so it's optional. And we'll ascribe it to as a property of the class. Self.medium index equals medium index.
So I've got a question. How do you differentiate between what you put as an input into the method, whereas what you leave as something that needs to be referenced with the self command?
Right. Usually there's some intuition involved. If you have to step back and think about what the object is that you're creating. So let's say in the case of, okay, this is a good one. So in the case of our sensor, right, our sensor might have equations for computing signal to noise. You'll have an SNR function, like your get SNR function. That function requires knowledge about the properties of the sensor, but it also requires knowledge about the exterior environment. Like how much light are you pumping into the sensor at once? Because that'll determine, the SNR performance of the sensor. And so in that case, you would distinguish, okay, I know that my pixel resolution, for the sensor is 640 by 512. That's a property of the sensor. And so that would exist within the sensor class. Versus if you think about the light coming to the system, into the sensor, that light is not a property itself of the sensor, right? That's independent of the sensor. And so you would pass that in as a function argument into that SNR function. You'd say light equals some amount of flux or radiance, right?
I see.
And right, so I forgot to put this under the init method. There we go. So this init function is instantiated anytime that we instantiate or create an optical surface component inside of our code. The last thing I'm missing here is my inheritance. So this class, as of now, only exists on its own. Like it doesn't inherit from a parent class. To do that, I need to pass in the parent class as an argument here. So I wrote this wrong. This should be, I think we said we would inherit from component. There we go. Of course, I have an imported component, so I have to import that using this. So I call in my import statements from architect.systems import component. There we go. I've found my init medium index equals none. Perfect. Oh, okay. Anyone know why this? Actually, sorry, that's just a typo. Never mind. Oh wait, no, it's not. Incident angle, incident index. What's the error here? Oh, let me do angle refraction. We'll split this up into two lines. Equals this equation we came up with earlier. I think I missed closing bracket. Okay. There we go. We're missing a doc string, but we'll get back to that. This init. Okay. Last thing I need before we finish the implementation, I need to call the initialization function of the superclass. So in this case, the superclass is the component class. Whenever you do this sort of inheritance, it gets a little funky because you need to also technically instantiate the parent or run the instantiation function of the parent. And so you do that within your init for this parent, for this object. So you call super.init. And normally we would pass in, well, for component, it seems like we need to give it our dimensions, our mass, our volume, our density. So let me just copy this directly. And of course, these aren't defined yet, but we can define them up here as arguments. Actually, in the interest of time, I won't do that. I'll leave it as this.
You slightly lost me a little bit. Can you explain again what the super thing is? I've never heard of that before.
Yeah, so you've got an initialization class, right? This is your constructor. This is the function that runs whenever you create an optical surface. So it's the function that accepts your arguments, such as medium index, whatever else you want. But we also know that component, like this parent class, itself has an init function here. And so typically what needs to happen is, if you really want this to be a proper child class of the component class, you also need to call the component's init function. And you do that by calling super.init and passing in any arguments that are relevant to the parent class. Does that sort of make sense?
Yeah.
Anyway, that's a technical detail. We'll move forward from here. Okay. Last thing I'll do before I finish this is I will, of course, write a doc string. And the way we run our, the way we write our doc strings might be a little different from what people may be used to. If you've ever looked at NumPy style or Google Doc string style for doc strings, we will actually put in the URL for this page I copied earlier, the URL to the specific equation card inside of the mathematical modeling database. So that's this one. Perfect. The reason we do this is, of course, so that our functions are traceable. So if we are ever, reviewing code or looking at code, and you ever want to see, like, hey, I don't quite understand how this equation is written out, you can always control click and follow it. It'll take you directly to that equation card inside of the modeling database. Of course, it doesn't in this case. Let me try that again. There we go. That's the right one. Cool. That makes code review super simple, a lot easier to handle. I'll show you that if we have time. But okay, so that's it. We've implemented our function inside of this nice class, optical surface. I'm missing a doc string, but I'll write one now. I'll do.
Just write placeholder doc string.
That can refract light. Perfect. Thank you, Copilot. Okay. Cool. Oh, this is incomplete. Get the angle of refraction for a given incident angle. Let's leave it at that. I forgot to make these nones because sorry, they're not nones, they're required. Last thing before we write our tests, because we'll get to unit testing in a second, is units. Okay, so we haven't actually touched units, but in Architect, we make use of this nice library called AstroPy. And let me import AstroPy. So import AstroPy.units as unit. We use AstroPy to handle all our units effectively. AstroPy in and of itself is not a library for handling units, but it comes with very nice tools to handle units. And the way we do this is within my angle of refraction, I'm going to add a type hint to this incident angle. The type hint is going to say I want this argument to be of type unit.degrees. I think deg is the short form. And I want this instance angle to remain dimensionless, so I'll leave it blank. And my return, what I'm doing right now, by the way, are these are called type hints in Python. They were introduced recently in Python 3.8, 9, 10, somewhere along there. Anyway, they don't actually they don't enforce strongly typed programming in Python, but they suggest to the developer that this is like to us, these are the units that we should expect to receive. And they're a little more powerful than that, but I'll show you in a second. My return is going to be, again, another angle. So I'll hint it as being a unit.degree. Okay. Am I still missing something? Missing class docstring. All right, I'll move this up here. Cool. What do I got here? Trailing white space.
So the linter thing you mentioned before, if you didn't like do all this formatting stuff, would it sort of like fill that in for you?
Yes, it would. All these blue underlines are being detected by the linter, but my auto formatter will take care of these when I run pre-commit anyway. So like this is pretty useless if I want to do this on my manually. But yes, the auto formatter will take care of all this, including sorting the inputs. Missing module docstring. Okay, that it won't solve. I need to do that manually. An optical surface component. Okay, so this script is looking pretty nice. Of course, whenever you write any piece of code, it's important, super important to test, right? To do that, we do something called unit testing. So similar how you might develop, test plans for TVAC, test plans for SNR, as part of your normal engineering workflow for building out your systems. You do the same in code. The principle stands. And to do that, we go to this other folder called tests, and we're going to create a new test file for this component specifically within the optical folder. Test optical. Let's make a new folder actually. Or you know what? For now, I'll put it under at the root right here. So we'll create a new file. Test underscore optical surface.py. Let me copy over some boilerplate from this other file. Test for optical surface. So docstring. We want to import the logging module. I'll show you what that does in a second. We'll import the units module again from MasterPy. But instead of importing optical component, we will import optical serve from systems.optical surface, import optical surface. There we go. Okay, so this is the first test I want to write. I want to write a test that confirms that we can in fact successfully instantiate this component. That's probably the first thing you'll ever test whenever you implement a new component. And so to test instantiation, I'll call the optical surface component, and that'll generate an instance of that component and feed it into my component variable here. All I want to do from there is log it. I want to print it to the console effectively to make sure that that worked. I'm getting an issue here. No name. Let's just run this and see what happens. So VS Code makes it super nice to run tests. You see this little play button right here on the left-hand side. I can just click that and run this particular test. If it fails, which I guess it didn't, we would see a readout of the error here, but it passed. Great. Okay, so we can instantiate our optical surface component just fine. And if I want to see what this log spat out for me, I'm going to go into the logs folder and open up pytest.log. I usually like to pin this, so it's always pinned to my view. We see here that I've printed the optical surface component. It's basically empty because it has no mass, it has no volume, no density, and it has this extra medium index property that we created. If you're wondering where these other things came from that we never defined initially, they are coming out of the parent class for optical surface, which is the component class. And so components all have physical dimensions, mass, volume, and density. So this is the thing that will be appended onto this list. when we created the optical surface definition. Cool. Okay. So that's testing. That's logging. The last thing I want to test, and we're getting close on time here, but I do want to test to make sure that this function runs. That was the whole point of this endeavor. So let's create a new function. Define test angle of refraction. I want to test the angle of refraction method. So again, I'll instantiate the component. I don't necessarily care about logging the component again. We know that part works. I'm going to define an incident angle for my ray of 45 unit degrees with an incident angle of, let's say, just one. Angle of refraction is going to be the return value of this function, component dot angle of refraction. So here I'm calling the method that we created earlier. I'm accessing it with the dot operator, component dot angle of refraction. We're passing in an incident angle. I usually like to declare these explicitly. Incident angle equals incident angle, incident index equals incident index. Okay. And then finally, I'll log it console again. Logging in this angle of refraction to see what angle comes out of the surface on the other side. The last thing, super important last thing, is this assert statement. So an assert statement in Python effectively checks to make sure that whatever conditional I put inside of the assert statement returns true. So in this case, I'm checking to make sure that the angle of refraction we're getting out is equal to, in this case, Copilot suggested 45 unit dot degrees. We actually don't bother specifying numerical values in our unit test. So what we actually do instead is check that the units equal the expected units on the return. So if you remember, I specified in the type hints of this function that I expect to receive degrees coming out of the function. And so that's what I'm testing for in my test function. Where'd it go? Here. That's what I want to test for, is I want to test to make sure that I am in fact getting degrees out of this function. The reason we no longer actually check specific numerical values coming out of these functions is that for very complicated functions, it gets very hard to do the computations by hand. So like in the past, one person would have to sit there and actually, do the math on their own. So for Snell's law, it's pretty simple, but for a more complicated equation like SNR, it can become pretty intractable to do it on your own, right? And so we decided that wasn't worth the efforts. Now we just check to make sure that the units come out properly. Whether or not the numerical values are correct, that's a different question. And we don't test that. We don't capture that necessarily with our unit tests. And so it's important to actually check after the fact to make sure that the units, the numbers you're seeing are to be expected.
So does this only work if it's like a single unit, or can you do a single like unit test if it's like sort of like a complex unit, or like the answer should be like, degrees over like meters times like seconds or whatever?
Yes, that is absolutely possible. So to build more complicated units, you basically just multiply these or divide or operate on them in any way you want. These are objects that you can manipulate. And AstroPy will fill in the gaps and realize, okay, I see that you want to create a unit, meter squared over kilograms. And then that's what it'll check for effectively in the end.
I see. Yeah.
Cool. Okay, so let's run this. See what happens. Again, click check, click the play. I think okay, so you've got an issue. We're getting an unsupported operand type for float and none type. Okay. So AstroPy tends to be a little finicky when it comes to dimensionless values. This is a bit of a weird one. Let me try explicitly making this. Actually, let me try removing the 0.0, recording that. Okay, let me try making this a unit.dimensionless unscaled. So this is going to declare it as, hey, this variable is in fact dimensionless. Okay, that doesn't like that either. Perfect. Okay, this is the great opportunity to show you guys how to do debugging in VS Code. So let's say your function doesn't work. Literally here it doesn't, and I don't know why. My first step, my first go-to is the debugger tool instead of VS Code. So to do this, I'm going to head over to the Run and Debug tab. I'm going to head into the function, and I want to set a breakpoint at this line. So this little breakpoint I put here will tell VS Code to stop running the program when it gets to this line. From there, I should be able to do some inspection of each of these variables within the debugger pane. So let's try that. Let's see how that goes. Again, we'll go back to testing. Instead of running it from the check mark, I'm going to specifically pull up this test and run it using the debugger. So this debug test icon. So this should stop me at my breakpoint. There we go. Okay, so it stopped the execution at the breakpoint. I'm seeing that I have an incident angle coming into this function of 45 degrees, which is what we expect to see. An incident angle of 1. And, ooh, okay. So I see, can anyone tell me what the issue is here? If we take a look at what has been declared and what hasn't been declared inside of this function. So I'll give you a hint. Let me pull up. What can I pull up? Self, systems, functions. No. Locals. Okay, it doesn't seem like I can pull up the relevant thing. Oh wait, no, I can't. Okay, I'm looking right at it. Yeah. Can anyone guess why this line of code is failing based on what you see here in the debugger? So our incident angle seems fine, right? That's this one we passed in 45. The incident index looks fine, but there's a third variable here that we haven't considered.
Because it's red.
No, well, okay, it's not self because that's just the code. Sorry, the color formatting.
I think
you're close. Oh, Connor, yeah, go ahead.
Yeah, the medium index is none.
The medium index is none. Yes, because we never defined it. Exactly. Yes, good catch. So this is where the issue is coming out of. We're telling NumPy to operate on none. And of course, you can't divide an integer or a float by none. That doesn't make sense. So if it's okay, how do we correct that? What can we do up here in our test function?
You just have to set a value to it, right? Yeah, that's it. So let's go ahead and do that. And I had to do that specifically within the optical surface instantiation. So here, because of course we define it as a property of the surface. The reason this is an issue and the reason we didn't catch this earlier is because I forgot to do one thing that we, Abir actually implemented it way back, which is we actually now have to write assert statements within the functions themselves to check that we have the correct properties coming into the computation. So I'll show you an example in, let's see, optical surface for optics. Here. So this is what an assert looks like within a function. We call these assert statements, or we write them to check to make sure that this doesn't happen, that any property we need to compute with within the function is in fact not none. And so that's what this is saying, is assert self dot some property of the system is not none, else tell the user, hey, you need to set a focal length for this to work. It's a quality of life thing mainly, as opposed to having to sit down and really have to think about what's wrong with the system. This would have been easier to catch if there was just a statement they're telling me to do so. So let me fix that.
I'll write this as an assert. Assert self dot. Of course, here we're checking for medium index is not none. And we'll say medium index must be set. Okay. We are at time. If anyone needs to get going, that's cool. I'll wrap this up in a few minutes. So let's run this one more time, and we should be told of what's happening with that assert in place. So now it should say assertion error, medium index must be set. Great, thank you for letting me know. I'll put it in. Medium index equals, sure, let's do 1.5. Run the same one more time. Okay, we got a second issue. Okay, so now we see a distinction in the units that we thought we would get out versus what we're actually getting out. It seems like the answer coming out of the function got turned to radians at some point, probably by NumPy, versus we expected to see degrees. So that's an easy fix. I can go back into the function and return angle of refraction dot to unit dot degrees. So this is going to be handled by AstroPy. We're telling AstroPy, hey, I want this quantity in unit degrees. So handle that conversion on your own as you see fit. So we run the one more time. Perfect. Green check mark. Everything passes. Last thing I'll show you is the process to actually push your code and put in a pull request. So let's say this is all good to go. I finished my code. I've written my unit tests. I've touched two functions here, or two files, and they are tracked inside of the source control tab. Okay. Next thing I want to do is write a commit message. So this is me telling the Git history what I did. We write these in present tense. Add optical surface component and unit tests. Okay, and we'll see what kind of magic comes out when we hit commit. This might take a second, but you'll notice something's changing in our file. It's being formatted. We now have a structure to the import statements. If you can see, they were separated into categories: standard library, external, project, and there was some white space removed, as well as some wrapping of the code, capping it to 88 lines. Cool. So the auto formatters work, but it seems like something failed. So let me take a look at what failed in the pre-commit. So you can go in here and check what failed. So isort failed. This is one of our auto formatters. So this will fix itself. Black, another formatter, failed, but it fixes itself. Autoflate passed, file upgrade passed. Doc formatter failed, again, fixes itself. Pilot is the only linter that actually would tell us if there's anything in their code that can't be fixed automatically. In this case, it seems like everything passed, including the linter. And so this typically happens because pre-commit won't let you push code until everything passes. So even if your auto formatters took care of fixing things, it'll fail so that you as the developer can go in and check that the auto formatters didn't break your code in some unexpected way. So now if I run the same thing again, it should pass because the formatters took care of these failures automatically. Let's take a look at that.
Is there any way to override that?
As in, if you wanted to say change this pipeline or skip things entirely?
Yeah.
Yes. Yeah. So if you have pre-commit set up, you'll typically also have a .precommit config file set up. So that's this one here. And here you can define exactly what you want this pre-commit pipeline to look like. You can have isort, black, autoflag. These are the ones that we found to be most helpful on our architect. But you could delete this entirely and pre-commit just wouldn't run. Or you could comment these out individually or delete them entirely and they will not run as part of the pipeline. Cool. Okay. So that worked. Oh, shoot. I kind of did this backwards, but before I commit, let me commit, undo last commit. So I'm bringing the changes back to my local machine. I actually don't want to push directly to main. It's usually not best practice to push to the main branch. Git branches are like a tree. Like you have the root of the tree is your main branch. This is where like your published code exists. And then individual developers might take on their own sort of parallel timelines for different branches to work on specific features. And then those features will get merged into the main branch at some point. So I don't actually want to push this directly to main because that's not best practice. I actually want to create a branch, put my code on there, and then ask or create a pull request that effectively asks someone else to check my code to merge it into main. So to do that, it's no problem. I can just go into here. The command I did to pull up the command window is Control-Shift-P. I'll do git, or actually, sorry, I can just click it in the UI. Click on main. I'll create a new branch. We'll call this optical surface component. This is the name of my branch. I'll publish this to Git. And now this code has been ported over. And you see GitHub is actually asking me if I want to put in the pull request, but I'll do this manually. So again, I'll commit it one more time. It's now being committed onto this branch specifically, so not main. And then we'll take a look at what this looks like on GitHub. Hit sync. Perfect. So now let's take a look at what that looks like online. Okay, so we see GitHub detected a change in this new branch, optical surface component. So let's take a look at all my branches here. So of course we have main, but we have this one that I created just now, optical surface component. So this is a completely parallel timeline to main. It's got all the entire repository exists on this branch, but with the addition of my changes. So what I want to do right now is create a pull request to merge my branch back into main. So a lot of description, add optical surface component unit test. I'm selecting main as the base, and I want to merge in my branch, optical surface component. This is where the whole code review dynamic comes in, is now I can't merge this on my own. I actually need to have someone come in and review my code. That's usually best practice in any sort of collaborative code environment, is you always want to make sure you have a reviewer that comes in, checks your code, determines whether there's anything that needs to be changed or gives you feedback on how you did. And so let's say I wanted Rosie to review my code. So let's add Rosie here as a reviewer. I'm going to assign myself to this PR because it's my PR. I'm putting it in. And for development, I'll show you this in a second. But anyway, so here's the code I added. Let me go ahead and create the pull request. So Rosie will now be notified that I've asked her to review my code. And you'll see that it won't actually let me merge until she's reviewed it and given me the green thumbs up. Last thing I want to do before I close off is select the ticket that I was working on within this development dropdown to tell GitHub, like, hey, this is a PR that's intended to resolve this pull request for this issue in the tickets panel. So now this ticket will automatically be closed when and if this goes into main. So that's it. That's the end-to-end. I showed you guys how to set up a poetry managed environment. You saw how to write, create a new component, a fresh new component inside of Architect. Showed you the class diagram inside of Architect. You learned how to write unit tests for that component, how to manage units, and of course, how to create a pull request to get your code reviewed. So now Rosie would hypothetically be able to go in here. Let's say I was Rosie. I could go into files changed, and I could review David's code. I could go in here and say, hey, I think you have the wrong URL for this reference. So let me add a comment. I think you have the wrong URL.
So anybody can do the review, right? It doesn't have to like actually be me that does it. It's just like that my name is tagged there. So I should be the one to do it, but like anyone can still go in and do this.
Correct. Yes. You are set as the reviewer. So if someone else reviews, it's fine. I don't know if GitHub will allow you to merge if you specifically don't also review. Like if you didn't want to review something, you'd probably just take your name off and swap it for someone else. I actually don't know if GitHub will let you merge if you aren't the one to review it at least once. But yeah. Last, very final thing. you might notice this loading icon happening in the background. We make use of GitHub Actions, GitHub workflows to effectively run a continuous development pipeline within GitHub. So what that means is that whenever you put in a pull request that's going into main, GitHub is going to launch a virtual computer somewhere in the world to run all the unit tests for the program. So effectively, it's going to check to make sure that you did in fact pass all the tests that you wrote. So here, you're seeing that it run a job. It's setting up the dependencies for the project like pre-commit, and it's running PyTest. PyTest is the library that we use to run our tests. So it's doing exactly the same thing as what I showed you here in the testing tab, but of course it's doing that on a separate machine to confirm or to verify that you're in fact not breaking anything on any code on main. And it seems like it passed, so that's great. The pipeline is passing. Blasting here would just be a review. So yeah, that's about it. Sorry I kept you guys a little later. I'm free for questions if anyone has any. Other than that, thanks for listening, guys.
Thanks, David.
Thanks.
Take care, guys.
David.